years, the focus of AI development was the individual model, scaling parameters and reasoning capabilities until an agent could reliably solve complex problems. But the moment those agents look up from their work and attempt to collaborate, the system breaks. Standard software integrations rely on REST APIs, which have functioned as the backbone of the internet for decades. But an API is a fixed contract. It requires a human engineer to read documentation, define exact data fields, and hard-code the integration at build time. The connection is rigid and expects a passive endpoint on the other side. Autonomous agents operate at runtime. They determine their specific needs in the middle of a task, often requiring resources they weren't programmed to use. This demands a system for discovering and negotiating with unknown peers on the fly. In the early stages of agent development, this led to a massive integration bottleneck. If an agent built in one framework needed to talk to an agent in another, developers had to write custom glue code for that specific pair. As shown on the left, 6 siloed agents require 15 custom links to stay connected. Scaling that entire system is mathematically expensive. The total number of connections grows with the square of the agents involved. But by adopting a single shared protocol, like A2A on the right side, those links become entirely linear and manageable. The industry solved this by moving towards a standardized communication language. Each agent implements the standard once, interfacing with any other compliant agent on the network. This enables cross-vendor interoperability. A Google agent can hand a task to a Microsoft agent because they read the exact same machine-readable specification, regardless of the frameworks used to build them. Shifting from hard-coded integrations to autonomous negotiation allows the network to scale without a human manually mapping every new connection. By 2026, this architecture stabilized into a 2-layer protocol stack, separating how agents talk from how they act. The horizontal layer is A2A, designed for peer-to-peer coordination. Now a Linux Foundation project, it standardizes collaboration primitives like agent cards. While A2A handles conversation, agents execute work via MCP. This vertical layer connects downward to tools, databases, and file systems. Originally introduced by Anthropic, MCP was adopted by every major AI lab and hit 97 million monthly SDK downloads by early 2026. It has become the foundational infrastructure for agentic tool use. These 2 layers are orthogonal. A2A goes sideways to find a partner, MCP goes down to grab a tool. They work in tandem rather than in competition. In a single operation, a planner uses A2A to hire a specialist agent, and that specialist uses MCP to reach into a corporate database. The protocols compose to solve the problem. They provide a negotiation layer above traditional APIs, allowing agents to navigate complex tasks autonomously. To understand how this looks in practice, we can trace a request to a travel planner for a flight and hotel in Lisbon. The travel planner receives the prompt and identifies that it lacks the specific tools to book travel. It needs to hire specialists. Step 1 is discovery. The planner scans for machine-readable agent cards, digital resumes that describe an agent's capabilities, and finds a flight agent. Step 2 is the task. The planner opens a unique task ID. Step 3 is negotiation. Rather than a static error, the flight agent pushes back, setting status to input required, asking to choose between a cheaper or shorter flight. This multi-turn interaction is the core benefit. The counterparty is an autonomous peer that asks for clarification rather than a passive endpoint. While flight negotiation is underway, the planner simultaneously tasks a separate hotel agent. Beneath this horizontal conversation, both specialist agents use vertical MCP connections to communicate with the actual airline and hotel booking tools. Step 4 is the artifact. Once confirmed, the agent returns the final ticket as a structured deliverable, and the task flips to completed. The planner aggregates these artifacts, presenting the final trip. The user sees a single result, but behind the scenes, 3 different agents collaborated through invisible handoffs. Protocols give agents a language, but developers need frameworks to arrange them into a functioning team. This is the kitchen brigade model. It organizes agents as a staff of specialists, using specific orchestration patterns to ensure work is predictable and safe. In a sequential pattern, agents act as an assembly line, passing output to the next. In a hierarchical pattern, a manager delegates subtasks and combines results. In a group chat pattern, multiple agents share a context window, debating until reaching consensus. Frameworks like Crew AI, LangGraph, and AG2 exist to enforce these structures, ensuring that agents stay within their defined roles. They also manage the transfer of state. If a general assistant hands a user off to a billing agent, the framework ensures the contact survives. By 2026, these frameworks converged on the core protocols. Whether you build in LangGraph or the OpenAI Agents SDK, underlying agents can communicate across boundaries. This turns chaotic peer-to-peer messaging into a structured, production-ready workflow. Despite the robustness of this architecture, multi-agent systems introduce failure modes that simply don't exist in single-agent environments. Trust remains the primary challenge. An agent card is a claim of competence, not a guarantee. Verifying that a discovered agent is legitimate and non-malicious is an ongoing area of research. Then there is the problem of identity. Managing permissions so that one agent can safely act on behalf of a human user across multiple third-party services is a massive security hurdle. Efficiency is also a factor. Every inter-agent message consumes tokens. In verbose architectures like group chats, the financial cost of agents debating a task can quickly exceed the value of the work performed. The most dangerous failure is the runaway loop. Without human oversight, Agent A can delegate to Agent B, who delegates to Agent C, who asks Agent A for clarification, creating a recursive circle that drains resources indefinitely. This is why the structure of the A2A protocol is essential. By mandating task IDs and lifecycle states, it provides the telemetry needed to audit, trace, and interrupt these conversations the moment a loop is detected. A single model is an individual worker. A multi-agent system is a functional organization. These protocols have established the foundational infrastructure for a network where software can autonomously discover, negotiate, and execute complex labor on our behalf.